Hi class, this video is for exploratory factor analysis, but we're going to do it in R. Exploratory factor analysis is a statistical technique, and we use it for dimension reduction and to explore the underlying structure of whatever measure we are using. So think about it this way: if you are using exploratory factor analysis for questionnaires, maybe you have 32 items in your questionnaire and you want to see the relationship between those items. So a good way to find out what relationship there is between the items is doing a correlation. But once you do a correlation for all the items, you're going to have like a 32 by 32 matrix, and then you have to look at this giant matrix with like 1024 or something correlations, and that's just ridiculous. So what exploratory factor analysis does is that it kind of reduces the dimension of that giant matrix, and then we can name those little, it groups together those correlations, and then we kind of name those groupings so that it makes sense to us why they're grouping together. And it's easier with social sciences because usually there's always a theory behind it. Another technique that does similar thing is confirmatory factor analysis, but exploratory factor analysis it has a lot more freedom, which can be a good thing or a bad thing depending on the situation. So let's talk about the types of variance that we're going to have when we do a factor analysis. So we can have the common variance, which is the overlapping variance between the items. So here I have the overlapping variance between the items. I have the unique variance, which is just what that single item explains, and we also call it error variance. And the commonality is just the common variance for that one item. And you can think about it as an R-square for that item. When you're doing EFA, it describes the common variance. When you're doing PCA, it describes both the common variance and the unique variance. So for example, here where we have three different variables that are overlapping, we can see that the commonality is going to be 1. But when we have this other variable that's not really overlapping with the rest of the items, we can say that the commonality is 0. So what are the kinds of resource questions that you can answer with an EFA? You can answer what's the number of patterns, or what's the number of factors or components that you have, how many fit the data if you don't know it, and does it match what's on the theory, or if you don't know it, this is how many factors this theory should have, maybe. You might want to develop your own measure, but you're not quite sure how those factors are going to come out, so you would do an EFA for that. You want to see how the questions group together, and sometimes it's easy. You think the questions are going to group a certain way, and then when you give it to a certain population, they interpret it differently. So you want to see how it groups for certain populations as well. And then what I think is one of the most important ones is, can I eliminate questions from this questionnaire? Because you always, people are overwhelmed with research and marketing sometimes. So if you can take away some of the burden from them of taking a long survey, you always want to do that. So our data example is going to be from a self-determination questionnaire that has 32 items, and we have data from 206 participants. It is in a CSV file, so you're going to use a text-based option for importing it, and make sure you select heading yes when you're importing, otherwise it's going to add a heading to the data, and that's not what you want, and it's not going to work. You don't want that. So self-determination theory is concerned with supporting natural or intrinsic tendencies to behave in effective and healthy ways. So people were obviously interested in college students. We are going to determine the factor structure. So theory tells us that there should be 3 factors for this scale. And we're going to see if that's true, if it fits for this particular sample. I actually put the scale here so I didn't have to give you a second document. And I bolded the items that need to be recoded, and I'll go back to this later. I just want to point out when you can see items that need to be recoded in the correlation matrix and the commonalities. So data screening first, as usual. I use the summary function, and here I can see I have missing data for a couple of them. Missing data. And I have exactly just the 32 questions. There's nothing else in this data file. So 206 participants, 32 questions. Did I check for missing data? True. I removed 8 participants because they skip a lot of a scale. The way I removed them was just using the na.omit. Look at my new dimensions. Now I look for outliers using my Mahalanobis distance code. Apparently I have 12 outliers and I need to remove them. The way I remove them is with the subset code. And these are going to be my new dimension. So I'm down to 185 participants, the same number of variables. So power analysis option is not available in GPower for EFA. What's recommended is that you have a large sample size, and there are a couple of rules of thumb that I will go over. So it's recommended you have 10 to 15 participants per item. As in general, 100 participants, anything less than 100 is not acceptable, and it's going to give you unstable solutions, and it's probably not going to get published either. Ideally, you would have north of 300 participants for you to run the EFA. And here I listed a couple of resources of research on what's the best combination of number of participants and number of variables for your EFA. The next thing we're going to check is the assumptions. So first I'm going to check the correlations between the items. I use the regular correlation function, and I store everything into a core fact variable. And then I print it out and I rounded everything to 3 digits because as it is, it's insane because we have 32 items. So imagine if I don't put that restriction, it would just look crazy. We are going to use the correlation matrix later. That's why I stored it here. So that's the correlations. They look okay. So I remember, for example, item 27 is reverse coded. So you can see how it's not correlating. It's not going to be correlating with the rest, with certain items. I was going to say the rest, but it's not all of them. So you can already see there's some items that need to be reverse coded. The next thing I checked, which is the determinant of the correlation matrix, I wanted to see that it was positive, and it is. And then I asked for the covariance determinant, and it was also positive. The reason I checked this is I want to see that they're positive, definite. That means that that's going to make the calculations possible for R and any software, really. And it tells you something about the linearity of the data. I also use this function rcore, and the reason I use it is to see the significance of the correlations, just to have a p-value attached to that correlation. I use this library. I have to give the data as a matrix, so I just put as dot matrix, and then I put the data. So wherever you see the p, that's where the p-value for the correlations are. A lot of these, they're just very small and significant. Next thing I'm going to check is normality, and I run my fake regression using my data and the degrees of freedom from Mahalanobis distance, and I get the standardized residuals from that and then the fitted residuals. And I went ahead and got fancy and I actually used this new library and the function ggres histogram just to make a nicer looking histogram. It's okay if you prefer the other one. And it looks fine. If anything, it might be a little bit bimodal, but I think it looks normal enough. Then I check for linearity using the QQ-plot option. And we could have minor departures of linearity. It's not crazy. We've seen crazy, and this is not it. The next assumption we are going to check is the homogeneity of variance covariant matrices. So we don't actually have a grouping variable. Remember, we only have the 32 items in this file. So the way I chose to check for variance covariance was just to plot the fitted residuals against the standardized residuals that we got from our fake regression. And it gives me this really nice plot, and it looks really good. Like, there's no real pattern. We don't want to see a fan here. We don't want them accumulated in a single area in the plot. It looks pretty It looks pretty good. Like, it's not a problem. Now we're going to go into the assumptions specific to factor analysis. So first we're going to check the KMO, Kaiser-Meyer-Olin criterion. It ranges from 0 to 1. Closer to 1, it's indicating that the sample is adequate for the analysis. It could be PCA, EFA. The way we obtain it is by running the path function, and it has a lot of output, so I'm going to $sign KMO. So I'm going to use the library rela. I'm going to run this function path, and then here it needs to be given a matrix. I could have actually just done this and stored it in a different variable to put it in here, but I didn't. We're going to give it the eigenvalue criterion 1. And this is the convergence criterion, so it notes when to stop, and you can just leave it like that. It's by default 0.001. So I stored everything into path.core, and again, it's a lot of output, so I just $sign KMO, and it's pretty close to 1, so I'm pretty happy with that value. That's telling us that the sample, the data that we have, it's appropriate for factor analysis. So another measure that we can use is the MSA. It's another Kaiser-Meyer-Olin measure of sampling adequacy or correlation adequacy. I find that correlation adequacy is easier to remember. They are, so because they're from the same people, they are somewhat related, and I think one is calculated from the other. And if you use Yamobi for EFA, it gives you both of them automatically. So it's a single value that also tells you how correlated the variables are in the data set, and you are trying to do an EFA, so you want them to be correlated. If there are insufficient correlations, then it means that EFA is probably not the best analysis that you could be using. If it's larger than 0.50, then that means that the sample and the data set are adequate for EFA. If it's below 0.50, you can remove the variable and then try again. So here I ask for summary path dot core fact, and I $sign MSA again because this path core fact has a lot of data, and yeah, it looks pretty good. They all seem above 0.50. So I just have this other function, so I don't actually have to look at this. I just do any, and then I put what I want to check, which in this case is the column of MSAs, and then I just want to check if they're less than 0.5. You can add less or equal if you want, if you're interested in that, and all of them are false. So that's good. It's another assumption that we need because everything was greater than 0.5 as recommended by, this is the Andy Field textbook. It's the citation I could find that had this cutoff. I really doubt he came up with it, but you can definitely cite that textbook. The next thing we're going to check, again, is correlation adequacy. We're going to do that with Bartlett's test. Remember, the null is that the variables are unrelated, and the alternative is that they are related. So here we're looking for a p-value that is smaller than 0.05. We use the library PSYC. We use this function, and we put our correlation matrix here and the sample size here. I store everything into BT just to keep things clean, and I really like the output of this function. It just gives you the chi-square, the p-value, and the degrees of freedom. So I reject the null hypothesis, and that means that there is a relationship between the variables in our data set, and that's what I want because I'm using a procedure that's counting on those relationships. So my KMO was close to 1, my MSA was, all of them were greater than 0.5, and my Bartlett's test was significant. So I think we have a pretty good sample, a pretty good data set for EFA. I can also check the number of variables. I have 32 questions. The type of variables, 1 to 7, they are at least interval. They might not be truly continuous, but we can say they're quasi-continuous or they're interval. And the sample size is pretty good. It's 185. It's not less than 100. It's not quite 300, but at least we have 10 observations for each item. So next we go into the data analysis. For our data analysis, we might see eigenvalues in the output. It's a mathematical representations of the variance accounted for by each one of the items and how much they're contributing to the factors. Sometimes we don't necessarily are going to extract them from R, but they are used for other procedures like the parallel analysis. Only a few of them should be large. And we have this rule of thumb that I should put here. If it's greater than 1, then that means however many eigenvalues are greater than 1, that's how many factors you have in your data set. The first thing I'm going to do is the parallel analysis. Parallel analysis, we use it to determine the number of factors or principal components that we want to obtain from a data set. It's based on a Monte Carlo simulation. It basically creates multiple data sets similar to the conditions that you give it. And then it tells you, based on all of these, the average, quote unquote, or the most common, quote unquote, solution is to have 2 factors or 3 factors or whatever it recommends. So when I was a grad student, you couldn't do parallel analysis in SPSS. I still don't know if you can, to be honest. But it's not necessarily something you have to do in R. You can just Google parallel analysis, and there are a couple of free options. Shiny, yeah, I think this is one. Yeah, you can just add your variables, sample size, type of analysis, and it will do it for you. For free. So that's nice. Jamovi also does it. So to do a parallel analysis in R, I'm going to use the FA parallel function. And I'm going to give it our data set, the number of observations, the method of estimation, which is going to be maximum likelihood. And there are other options. So if you need them, you can just Google the function and see what other options are available. And then in FA, I'm going to put FA for factor analysis. If it was principal components, I think it's PEC or maybe PA. So you do have to change this to factor analysis. And then it gives you this really nice plot. So here we're looking for the elbow and the graph. It also marks where the eigenvalue is 1. Remember, on this side we're going to have eigenvalues, and over here we have the number of factors. So if we just look at the anything above the eigenvalue of 1, it's recommending 3 factors. And if we look at the elbow, it's also recommending 3 factors. And it actually has this really nice output that tells you the number of factors it recommends. And it's telling you that the parallel analysis recommends 5 factors. So based on the eigenvalues, I see 3 factors. Based on the parallel analysis, I see 5 factors. And based on the theory, it was also 3. If we look at the output that comes with the parallel analysis, it has a section for eigenvalues, and you can see there's only 3 of them that are greater than 1. So that's what the eigenvalues are recommending, 3 factors. I kind of went over this already. The theory is recommending 3 factors, parallel analysis is recommending 5, the eigenvalues are recommending. So the next thing I want to look at is the scree plot, but before I do that, I'm going to run the actual factor analysis. I'll go over the options later, because right now what I want to show you is the scree plot. So the scree plot is very similar to the parallel analysis. It's going to give you a graph, and we're going to look for that elbow. It doesn't do it for multiple data sets, it just does it for the one that you're giving it. And it's based on the eigenvalues as well. So I'm going to use plot. And then I give it whatever's stored from the factor analysis function. Type B, and this is just how the graph looks. There's 2 2 or 3 types. I chose the one that looks the least worst. This just tells how big the graph should be. The main title, the X label, and the Y label. So the scree plot, I would say suggesting 2, maybe 3. You could argue for 3, especially if you focus on the eigenvalues. But it's definitely inconsistent. So theory says 3, parallel analysis says 5, eigenvalue says 3, scree plot says 3, you could argue for 2. So you can see it's normal not to have them agree. Of course, it would be easier for us if they agreed, but that's just not real life. So now we're going to look at the actual factor analysis procedure. We actually already ran it, and we used the eigenvalues that were calculated in it to create the scree plot. So now we're just going to open up where we started to look at all of the output. Before we look at the output, I just want to talk about the rotation, and I want to talk about what you're going to see in the output, which is the commonalities. So factor rotations, you have 2 options. The rotation can be orthogonal or it can be oblique. So the orthogonal rotation, the factors will remain perpendicular, and it's ideally used for when your factors have to be uncorrelated, which might not make a lot of sense to you, but there are sciences where you would want it not to be correlated. And the method you would use for that would be Varimax. The oblique rotation allows the factors to not be perpendicular, and because it's doing that, it's allowing them to correlate. And the methods for that, there are Promax, which is the one that I use, and there's also Oblin-Min, which I think Jamovi and both Jamovi and R have that option. So back in the day, when statisticians first introduced EFA, it was an issue to have the factors correlate just because it's difficult to model. Remember all of the assumptions that we checked in this class, we always have to check that positive definite. We always have to check the determinant is greater than 0. If it's not greater than 0, then they cannot actually do the calculations that are required. So once they are correlated, if they're too correlated, you can have issues in the mathematical aspect of calculation. It just makes the model more complex. So back in the day, they kind of advocated for not having correlated factors. However, in the social sciences, I think that you want to have those correlations. You want to model those relationships. So for us, it just makes sense to use either Promax or is what I was talking about. When you look at the orthogonal rotations, you are essentially, you're going from this axis and then you're rotating it, and it's not really moving. It's maintaining the same distance in the axis, and you're just looking at it from a different angle. And over here in the oblique, you are kind of putting together, you're closing the distance between the 2 axes, and you want to keep them together. You want to model the relationship between those 2 factors. So for us, it's always going to be oblique. So we already discussed the commonalities, but here I just want to show you how it's going to look in the output for R. You're going to have a column for H2, which is going to be the common or share variance from the items contributing to the whole variance for the factor structure. And U2 is going to be what's left. So here in the diagram, you can see the commonality is how much these 2 items, Q2 and Q3, overlap, that's H2, and how much they contribute to the variance of the factor structure. The U2 is just how much the item itself contributes to the factor structure. So both are important. The one where it's just the item, we call it unique because it's from that single item. And also we can call it residual variance. The commonality, because it's 2 items, we call it share variance. And this is going to happen also in principal components. The output looks very similar. So here's where I ran my factor analysis. We actually already did this. I just want to talk you through the rotation. We're going to use the estimation method, maximum likelihood. I'm going to ask for 3, and the reason I put 3 in here was because I'm still going by the theory that we had 3 factors. And then I just put my data here, and I store everything in f dot no out. And we ran this already, so I'm just going to open it up. And this is what my output is going to look like. Here in the output, I want to point a couple of things. First, I want to point out that we are looking at the pattern matrix. I want to point this out just because if you do an EFA on a different software, it may print a couple of matrices and confuse you. So you're looking for the one that says pattern. So here it has the 3 factors. For some reason, they're flipped. I don't know, R is weird like that. And then it has the commonality and then the residual variance. So what I want to look here is that it's definitely contributed to a single factor. I don't want to see the question loading highly on all 3 factors or on 2 factors. It just means that it's not discriminating very well. So when people read it, it might be confusing them. It's just not working the way we want it. We want it to load on a single factor. So here for question 1, it's definitely loading on factor 1, not so much on 3, and even less on 2, and even better, it's actually negative. So it's going in the opposite direction. So it's doing a good job at discriminating here and falling into the first factor. Same for question 2. So it loads negatively in factors 1 and 2, but on the third one, it's loading pretty well. The cutoff that we're looking for here is anything above 0.30. If it's above 0.30, then it definitely it needs to be considered to be in that factor. So I highlighted an item that I thought it could be potentially problematic, which is question 12. And here it's about 0.30. And by the way, that cutoff comes from Tovashnik and Fidel. I didn't just make it up. It is about 0.30, but it's definitely loading highly in the first factor. There's no rule of thumb of how much more it needs to load in another one. I wish there was. It would make our life easier. So this could be potentially an item that we remove. This one doesn't worry me as much because it's clearly loading in factor 1. But if you look at 24, it's not loading as highly on the first factor. It's also loading on the third factor. It's definitely not on the second one. So I would suggest we remove 24, at least for teaching purposes. Next, we look where it says proportion of variance, and this is how much each factor explains out of the total variance for the total factor structure. It also gives you the correlations between the factors, and I'm going to go back to this because we can actually find these correlations, but if we use the HMISC function, we can also get the p-value for it. And then it gives us a lot of output similar to the confirmatory factor analysis output, but we're not going to use it for EFA. So if I'm looking at the output from the FA function, this is how much variance each one of those is explaining, each one of those factors. And we decided that item 24 could be problematic, so we can just drop it and run the factor analysis again. You could do it this way, just creating a new data set and storing it in a new variable, or you could just do it within the function so you still have your original data set intact. I asked for 3 factors, use the rotation promax, maximum likelihood. So this time I'm going to use the print function. I'm going to call the function where I store everything from the factor analysis over here. I'm going to $sign loadings because I'm interested in the loadings. I'm going to ask it to suppress anything that's lower than 0.3, and I asked to sort it. So side note, for APA, you actually do have to show all the loadings, even though it looks kind of busy. So you could just ask to remove this. The thing is going to keep them sorted, so it's up to you if you want to have them in order or not. But you could just play with the options to give you what you want. Okay, so when I look at this second factor analysis that I run, there's this item that is cross-loading, but it's definitely going into factor 1, so I'm not too worried. It's barely loading in factor 3. Same over here, it's barely loading in factor 3, it's definitely going in factor 1. So I don't have items that are cross-loading anymore. So I'm happy, it looks pretty good. And the next thing I can look at is the internal consistency reliability. So for reliability, we are going to use convex alpha, which is the most popular one. It is recommended that you have more than one measure of reliability. You can use McDonald's omega, or you can use Gutmann's lambda. That's another one that's popular for small samples. But if you're going to publish, I strongly recommend that you use more than one measure. So convex alpha is used because it's popular, it's available in a lot of software. It ranges from 0 to 1. The closer to 1 indicates better reliability. The issue with it is that it tends to underestimate reliability. So what I did next in the code was, first of all, I excluded item 24, and then I put the items into each factor as they came out from the FA function. So I'm going to use the package PSYC, which is here, and I'm going to use the function alpha, and inside I'm going to put no out, and I just want the columns inside of factor 1, which are those. So this little 2-column thing that I have going on, it would be the same if I type library parentheses psych and then I type the function. It just does the same thing as typing library. For some reason, R has moved on away from just typing library. We type less and less, and now we use the double column. So let's look at the output. So here's the actual alpha estimate, and it gives you a lot of other information. It gives you the alpha if item deleted. So it doesn't matter if the items here, we cannot drop them. The alpha would stay the same. The next thing is the item statistics, which I personally do like to put in papers. I like to put the N and the mean, the standard deviation for each. Another thing that I like about this output, it gives you the actual frequency of how many people responded into which category. So I really like that. And you can have issues when a lot of the people just don't use a certain category. Like that can also throw away your estimations. But that's a different class. That's a measurement class. So now I do the same library psych, but instead I'm using the double column alpha, but I'm going to do it for factor 2. That's my alpha. If I deleted, there's nothing that I can delete that can make it better. And finally, I do my alpha for factor 3. So the issue with factor 3 is that items 6, 8, 17, and 27 should be reverse coded. So you have two options here. You can use the command keys equal and then have the vector with the columns that need to be recoded. I personally just like using this one, check.keys equals true. I'm telling the function, you check if I have reverse coded items. I don't care. And then it finds them. This is my alpha. And then it's funny because it actually found the opposite. It found the ones that do not need to be recoded. And that's what this is the alpha if item deleted. And I actually tried it without the check keys option, and it doesn't realize that it needs to be recoded. It gave me something very low here, and that's how I know that the items need to be recoded. The next thing I look at are the factor descriptives. So I already created these variables that had all the items in there for every factor, and I'm just going to select each of those columns, and I'm going to ask for the mean here. I'm going to use this apply function, apply the mean to this subset of the data set, and I'm going to store it into my data by using $F1, $F2, $F3, and what's going to be in there is just the mean. So I can use the summary no out again, and it gives me all of the summary for all of the items, but if you're going to see at the end, I have 3 new variables for the factors. So now I have the mean for each factor, and I can just do standard deviation no out, $factor 1, and that's going to give me the standard deviation for each of the factors. So I can report that as well. So the output from the FA function actually gave us the correlations here. So we had this already. What we didn't have was the p-values, and that's where the HMISC function comes in handy. You can just put the data in there and then ask for the correlations. if you need the p-value. If you don't need the p-value, you can just use the previous one. So the next thing I'm going to do is just name the factors. Remember, we're doing a self-determination questionnaire, and we just want to name the factors. And this doesn't have to wait until the end. You could do it right after you remove items and you decide, you run the ifig and you decide that's the factor structure you're going to use. So a couple of items from factor 1: because I experienced pleasure and satisfaction while learning things, to show to myself that I can succeed in college studies. For the pleasure I experienced while surpassing myself and my studies. Okay. So this factor is actually called measure intrinsic motivation. Factor 2: because I need a degree to get a good job. That's very realistic. Because college provides me with a better understanding of the profession, which will be mine. That sounds awkward. Because I had to go to college in order to complete my degree. I'm not sure what's the difference between 2 and 13. Because it is a prerequisite for getting a job. So this is the career goals factor. That's what the researchers called it. Factor 3: because it's one of the ways that I have chosen to acquire skills in an area which is important to me. I wonder what I'm doing in college. I actually find it boring. Honestly, I don't know. I truly have the impression of wasting my time in college. So this one is, they're doubting their motivation for college, basically. So that's what the factors were loosely labeled. And I did put it here on the notes, so don't worry. Let's look at the write-up next. So I mentioned what procedure I was doing, the factor analysis, the type of questionnaire, what assumptions I screened for, the normal ones, homogeneity or variance, etc., and the new ones as well, which is the KMO, the correlation adequacy. I don't see it here, but you can also put the MSA. I mentioned how many factors the parallel analysis and the scree plot recommended. Then I mentioned the item that I removed, which was 24. I went into naming the factors, and every time I name a new factor, I kind of made added an item as an example. And then I went into Cronbach's, the reliability, and the means and standard deviations between the factors. You can add the correlation table between the factors. Remember, I always suggest to use one more, other than Cronbach's, another measure of reliability. And I'm actually going to give you the page on the APA manual where you can find the sample EFA table.